Hey, Preston.
Hi, Dr. Tran. When you have a chance, can you look at my problem for 4B? It's the last problem on the homework.
Okay. Yeah, let me get set up here
Okay.
and then we can take a look. Okay. Do you have it on your computer or you can share screen?
Yeah, I do.
Okay. All right, why don't you go ahead? Or let me enable it first. All right, go for it.
So what I did is I was finding the yeast integral first,
Yep.
and but so I put it on the integral calculator just to see. So my result I got here is the same. It's just,
Okay.
or it's correct, but is the setup, would I do 9 to 18 based on, like, this starts at 9 and then this is at length 18 meters?
Mhm. Yeah, it's a good question. So for this one, you would actually just do 0 to 9.
0 to
Uh,
9.
yeah.
Okay.
Um, yeah, that would be the best thing for that.
And then L would be 9 as well. So 0
Correct.
to 9 and L. And then I find F and M, all those.
Yep.
And then I set up the global matrix and my, I don't know why it's glitching out. But
Mhm.
basically it would just have the fixed constraint at the wall, correct?
Yep. Yep. I taking a look at your nodal forces. Maybe this is a function of you doing it from 9 to 18, but
Mm-hmm.
both of your f's should be the same. So both your f2y and
Yeah.
f3y,
Okay.
because it's a uniform mode, and so that both of those should be the same. So,
Okay.
but yeah, maybe when you change the integration bounds, I think it should
Yeah, I
hopefully.
initially did 0 to 9 and I was still getting different answers, but I
Okay.
can try it again.
Okay, yeah, those two should be identical because it's a
Okay.
uniform. And then your moments, they should be equal in magnitude, but one of them is negative and the other is positive. So um
Okay. Okay. Thank you.
yep.
Why is it 0 to 9 and not 9 to 18? That's how I did it.
Yep. I maybe actually maybe for this one it doesn't matter because it's a constant mode. But it's just the standard is just to go from like you start from 0 and then you go to the length of the element. So that's just kind of how it's defined. Yeah.
Yeah, it's because I was the way that I trade was treating it was like we were working on the bar and
Mhm.
we had the initial conditions on that bar alone
Mhm.
instead of starting from the fixed position.
Yeah, maybe it does work, but I know when I did the solutions, I did 0 to 9 on that one. I don't think I've tried it with 9 to 18. But I think because of the cubic term, I would think that it would be, or because you have nonlinear terms in your displacement equation, then I think it would throw things off if it was not from 0 to 9. Yeah.
All right, I'll try it with 0 to 9 because I didn't end up with the same answers anyways.
Oh, okay, okay.
How was your weekend?
It was good. Extra hour of sleep was nice. Definitely well needed. But it's very dark now. Although I think that's the comment that literally everyone makes after daylight savings. Yeah, it was good. How was your weekend?
Very busy. Yeah, just trying to get your homework out of the way and studying for a circuits midterm that I'm probably gonna fail tomorrow.
Oh, oh no.
Yeah, that's really tough. I really hate the class.
Oh, yeah. Circuits is tough.
Dr.
Well,
Trent,
best of luck.
Dr. Trent, would it be possible to push back the activity 5 deadline until like over Thanksgiving break or after?
Yeah,
You
I
have
can
an,
I can I can do that. You want to have it due after Thanksgiving then? Because I
uh,
think our next one's probably not going to be until, let me see.
yeah, just because we have the midterm on the 18th.
Yeah, that's true. That's true. Okay, yeah, our next activity is not until the end of week 15. So let me go ahead and push it back till after Thanksgiving then,
Okay,
which is going to be
thank you.
when, let's see, I'll have it due on Wednesday, December 1st. How's that?
Yeah, it's a lot better. Thank you.
Okay, all right, let me do that right now. I'll update the PDF when I get back to my office, but I'll at least update the due date here on Canvas.
I like the play on words.
They what? Oh, yeah.
Oh yeah, I wanted to ask about the homework.
Mhm.
For the conceptual answering, for part C, define an element stiffness matrix, explain what it represents for a finite element. Do you want us to literally like explain it as in words, or just like draw up the matrix and then say what it is? Or
There's kind of a conceptual understanding of what the finite element or what the element stiffness matrix represents. And so I would want an explanation in words for that.
okay.
Mhm.
And I was also a little stuck on part D, just trying to understand how to solve for that.
Part B.
D, dog.
Oh, D.
Yeah, gone over direct stiffness method, solving finite element problems. Explain the process, how the process differs. Like,
Ah. So think about like just in general, like if you're setting up like an ANSYS simulation, what are the steps that you generally follow, right? So
right.
you assign material properties, you do the mesh, you do the boundary conditions, and then you solve. And so compare that to how you're solving these kinds of problems here, where
Okay, I
you're
see.
where you're basically doing everything by hand, but even by hand you're following kind of a set recipe of a step to do. And so at the end of the day, both you're getting kind of the same result. I mean, in theory, but just kind of compare and contrast of how ANSYS kind of presents that to you versus how you do that by hand.
Okay, cool. One more thing that I want to ask for the midterm, how are we going to solve the matrices? Are we going to be like supplied MATLAB, or do you just want us to set up the global matrix and then just call it a day? Or
Yeah, you just have to set it up, and so you don't have to
Okay.
do any solving at all.
All right, cool.
Any 8x8s planned for that?
Was that?
Is it any 8x8 matrices planned for that?
I don't know. I haven't written it yet. But,
Wrong answer.
Yeah.
We're gonna be here for a while.
probably not, because because if you guys are writing in 8x8s, then I have to grade in 8x8, which is what I don't want to do for the exam.
That's exactly what I was thinking. I don't want to make it too hard on you.
You're so considerate. I appreciate that.
No problem.
Those 8x8s. Oh my god, they took up half of my day.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing on this very dark evening because of daylight savings? It's been good, hopefully. I know everyone's kind of suffering a little bit through the homework assignment, and so I did warn you that it was a tough assignment, and so I know it's a lot of calculations and a lot of big matrices, but that's the only hand calculations I'm having you do for the class. And it's all in good preparation for the midterm too. Okay? And so if you've had me for a previous class, kind of my style is I push really hard on the homework assignments, especially the ones that require calculations. And so that's by design. And so my goal is that you work really hard on the homeworks, and then by the time you get to the exams, the exam questions are always a step down from the homework problems. And so that's kind of my hope with that. Okay. And so to answer a question, before the lecture, because I know some people are still kind of coming in for the exam next week, I'm not going to ask you to actually solve any of these systems because that would require MATLAB or some kind of, or you have to be really good with your graphing calculator, which I know some of you are, but not everyone is. So for the exam, all I'm going to ask you to do is just set up the equations. And so basically the way the problem is going to go is I'm going to give you the problem geometry. I'm going to give you the properties. I'm going to ask you to compute the element stiffness matrices, assemble it into one global system, and then apply the boundary conditions, and then that's it. And then that's the problem. Okay. So hopefully that will ease some of the calculations that you have to do for the exam. Okay. Okay. And remember, Thursday is a holiday, and so this is the only time we're going to meet this week. And so the next time that we meet is going to be next Tuesday, which I don't even know what we're doing. What are we doing on Tuesday? I think we're talking about meshing on Tuesday. Yes. Okay. Yeah. So on Tuesday we're going to start talking about advanced meshing. I actually do have a long set of lecture notes planned for that one, but we'll probably just cover a small subset because we don't have that much time. But that's what we're going to do then. And so Thursday, remember, enjoy Veterans Day, or maybe use it to get some rest or catch up a little bit. Which I think is going to be a welcome break at this time. All right, but for today, the subject for today is we're going to be doing another ANSYS activity. Okay, and so we haven't done one in a while, and so this is going to be the first one, for a while. I will say that this is probably one of the more chill activities, and so there's, I'd say there's a lot less to do with this activity than there are for the other ones. Mostly just because of the timing of the activity, because it's coming at a time when I know everyone's working on the problem set, they're studying for the exam. And I know the final project is out there too. And so I wanted to have an activity that was a little bit more on the fun side, but less on the, you have to do a bunch of simulations and ANSYS. Okay. And this due date is updated. And so it's no longer due on the 19th. And so I pushed the due date back to after Thanksgiving. And so our next activity is going to be on December 4th. And so that's going to be the first, December, what is it? Yeah, December 2nd, I'm sorry. So the next activity is going to be on December 2nd. And so this activity is now going to be due on December 1st, okay? And so that's going to give you an extra couple of weeks to do this activity. Okay. So hopefully that gives you a little bit more flexibility in terms of that. Okay. All right. And so I think that's all of the announcements I have to make. Are there any questions I can answer before we get started with the activity? Okay. All right. And so so we're going to learn how to do dynamics. And so, while I'm kind of giving this intro portion, if you guys want to open up ANSYS Workbench, and if you want to download the CAD file from Canvas, I think now is kind of a good time to do it, okay? Because it always takes a couple minutes to start up ANSYS, right? But just like I just mentioned, the activity today is we're going to be simulating a car crash, okay? And we're going to be using a very different module within ANSYS that we haven't used before. And so we're going to be using the dynamics modules in ANSYS, which is going to be very different from the static structural that we do, okay? And just like we mentioned last week, that the thing with dynamics is that it's actually a very complicated, very deep subject area. And what we're covering in this class is kind of the basics of the basics. And so we're only going to be able to use it for very kind of, I think I'd say very niche situations. But even then, you can still do some really cool stuff. And so one really cool thing that you can do is you can simulate impact situations where you have one object colliding with another object, and you can see how the object's going to deform, how the stresses are going to develop within the object. Okay. And so that's what we're going to do. And so we're going to simulate a car crash. Okay. A question. So is the project proposal still due on Sunday night? Yes. Yeah. So the project proposal is still due on Sunday. Mostly just because I want to make sure I get feedback to you before Thanksgiving. And so I want to have it due on Sunday just so you can start kind of working on that, because the project's going to be a fair amount of work as well. Okay. All right. And so the weird thing about this car crash is that, normally what you would expect is that when you ram a car into a wall like this, the entire car is just going to crumple on itself. And so we're actually not going to see that. And so, because we're assuming linear dynamics all throughout, what the car is going to do is going to hit the wall. It's going to kind of squeeze a little bit, and then it's going to bounce right back. And so it's going to be almost like the car is made of jello. And so it looks kind of funny. And so I will say it's not the most realistic simulation of a car crash. But I wanted to introduce the tools to you guys, and and just so that that you can do dynamics in ANSYS. But there is kind of a lot more that you would need to learn to really make an accurate simulation. Okay. Okay. All right. So let's go ahead and get started. So let's go ahead and open up Workbench. Okay. And so here is our familiar case here. Okay. And so normally at this point, we take static structural and we drag it over here, okay? But we're not going to do it. We're not going to do a static structural simulation. And so what we're going to do instead is an explicit dynamics, okay? And so we're going to take explicit dynamics and drag it out over here, okay? And then for the geometry, we're going to import the car crash geometry that you downloaded from from Canvas, okay? So let's go ahead and browse, and you should be able to load the car crash analysis.igs. Okay, and that should import with no problem. So it's an IGS model. Okay. All right. So before we jump into ANSYS Mechanical, let's go ahead and add some material properties. And so I'm going to go ahead and double click engineering data here. Okay. And we need to add two materials. And so we're going to need to add aluminum alloy, and then we're also going to add polyethylene, which is a plastic type material. Okay. But we're going to do this in a little bit of a different way, because normally when we add materials, we click here and we add a name, and then we define the properties just like that. But for this activity, I wanted to show you the ANSYS library of materials that they have. And so if you have kind of a fairly common material, you can just grab it from the library. Okay. All right. And so we're going to click on this button right here called Engineering Data Sources. Okay. And so it's the button next to the books on top. So let's go ahead and click that. And then after you click engineering data sources, you'll be greeted by a list here, okay? And so these lists, each of these is a different list of materials. And so if you click on a list right here, okay, so let me click on this, okay? And so if you click on ANSYS Granta Materials Data for Simulation, which is a sample, and you can go to the middle here and you can see all of the different, materials that they have in this particular library, okay? And so they have quite a bit. And so they have things like air, alumina, aluminum alloy, brass, bronze, so on and so forth, okay? And so we actually do want aluminum alloy, but the one that we're going to use is actually in general materials. And so let's go ahead and click general materials. And then you're going to go to row 4 right here, which says aluminum alloy. And then you're going to click on this plus button right here. Okay. And so what that plus button is going to do is that it's going to add this material to your project so that you can have it available for you in ANSYS Mechanical. Okay. And so after you click the plus arrow, you should see a little book next to your aluminum alloy. And so that tells you that the material was successfully added. Okay. So go ahead and do that for aluminum alloy. And then you're also going to do it for polyethylene, which is down here. Okay, so we'll go ahead and click that plus arrow. Right, and so you should have a book next to polyethylene. You should have one next to structural steel, and you should have one next to aluminum alloy as well. Okay, and so if you click on this engineering data sources again, and you'll minimize that menu, and what you'll see from your list of materials is that you should have aluminum alloy, polyethylene, and structural steel all together like this. Okay. All right. So is everyone able to add these two materials? Yeah.
Would that have worked for when we do the static structures as well?
Oh yeah, absolutely. Yeah, this works for static structural as well. Yeah. Yeah. So if you're for your final project or for anything, if you want to look at the library of materials here and see if there's one that matches your application, you can just go ahead and use that here. Okay. So I didn't show you this at first because I wanted you to get used to adding the material by custom, because a lot of applications you're going to be using custom materials, because a lot of companies, they kind of use their own materials for things, and they maintain their own databases, and so it's good to know how to add a custom material like that. Okay, any questions so far? Okay, all right, and so let's go ahead and we're done adding the materials. So let's go ahead and close A2 engineering data. And then let's double click on model right here to open up ANSYS Mechanical.
Sorry, real quick. Under the engineering data sources, where did you go to get the full menu or the full list of the material?
Oh yeah, and so if you click on engineering data, oops. A second. I think mechanical is still loading, but basically after you click engineering data, then if you click on this button right here called engineering data sources, it's kind of near the top. And then circle that. You click on engineering data sources, and then you're going to click on each of these is a different list of materials. And so where I went was general materials, and under general materials, you can see the full list right here. Yep. Yep.
I think on my end, I just see
Okay. All right. So let's go ahead and open up mechanical. Okay. And you can see here we have our car crash geometry. Okay. Oops. Okay. All right. So first thing we're going to do is we're going to set the material for the car. Okay. And so if you click on this plus arrow next to geometry, you can see here that we have two parts. Okay. Part 1 is the car, and part 2 is the wall. Okay. And so we don't really care about the wall because we're not going to be solving anything really on there. It just needs to exist for our car to crash into. But we do care about the car. Okay. And so first thing we're going to do is we're going to change the material of the car. And so we're going to go down here. Okay. And then under material, we're going to click on this and then assign it to be aluminum alloy. Okay. And so this makes sure that we're using an aluminum car. Okay. All right. And so there's that. Okay. Next we come up to meshing. Okay. And here the meshing is going to be interesting because we have two parts here. Okay. So we have the wall and the car. And so let me do this. And so let me go ahead and insert a sizing object, and I'll do one for the wall. Okay. And I'll insert another body sizing for the car. Okay. All right. And so for this particular simulation, we don't really care what's happening to the wall, and so we can use a fairly coarse mesh there. And so let me go ahead and apply a mesh size of 30 for the wall. Okay. And then for the car, we're going to use a much finer mesh here, and so let me use a mesh size of 5. Okay. And so before you mesh, if you go to the global settings for the mesh here, you'll notice that the order for the elements is kind of set to linear, okay? And so that's a little bit different than what we're used to, because normally for structural simulations, we use quadratic elements. But for dynamic simulations, mostly because of the cost associated with them, with forming and solving the equations, we're limited in this case to only just using linear element order. Which is okay. And so it's it's not that big a deal for this one. But we just have to make sure that we have a pretty good mesh density on our car to make sure our solution is going to be accurate. Okay. But I just want to make you aware of that, just so you don't go trying to change that. Yeah. Question.
Could you show body sizing again?
Oh yeah. And so for body sizing, I right click on mesh, and I click insert, and I click sizing, and then I selected the body that I wanted to do.
Oh,
yeah. Mm-hmm. All right. And
what size mesh did you put on the car? A 10?
I put 5 millimeters.
Oh, 5 millimeters.
Yeah. And so you'll notice that this is a pretty tiny car. This is basically like a Hot Wheels kind of car. Or maybe it's bigger than Hot Wheels, but much smaller than a real car. And so, just kind of keep that in mind. Okay, and so I'm gonna go ahead and generate the mesh, and let's see what comes up. All right, and so this is the mesh that results from mine. Okay, and you can see here that even with this, I'm kind of pushing it a little bit, and so the number of elements that I have is about 28,000. Okay, and so that's kind of as expensive as I wanted it to be. All right. Okay. And so another thing too is that if you read the problem specifications on the online, you'll see here that I mentioned that you should do a mesh convergence test. You can just go ahead and ignore this, and so you don't have to do extra part 3 of problem 1. Okay. But if you do, I will give you extra credit, but this is not required. I will say that it is a little bit tough to do a mesh convergence test on this one, just because the simulations kind of take a little bit of time, and so they're not going to be as fast as a static simulation. So if you do want to do this, just block off a good portion of your day in order to get the data required for this. Okay. Any questions? Any questions so far?
Yeah, for the size for the wall, did you use 10?
For the wall, I use 30.
30?
Yeah.
And then they're both left as linear?
Yes. Yeah. Yeah. Mm-hmm. All right. Okay, so that's the mesh. Okay. Next thing we have to do is the modes and the constraints. Okay. And so the interesting thing about this problem is that we're not actually going to be supplying any load. And so the only load that we're going to supply is we're gonna add a velocity to this car in order to crash into the wall. But we're not going to apply any kind of forces. Okay. But we do need to apply a fixed constraint on the wall. Okay. So let's go ahead and do that first. So I'm going to go ahead and right click on explicit dynamics. I'm going to insert a fixed support. Okay. And I'm going to change this to face selector mode. And I'm going to select all the outer edges of all the outer faces of the wall. Okay. Oops. Okay. All right. And so this will make it so that the wall is going to be fixed from the outside. Okay. And so the reason I'm doing this is that we're basically assuming that this concrete wall is part of a much bigger wall, and so we're assuming that there's kind of extra wall over here, okay, and that there's extra wall over here, okay, right, and and so that's why we're fixing it on the side to kind of simulate that fact, okay. Another good reason why we're fixing it on the side and that we're not fixing it on this face right here. Okay. And so this face right here is the contact surface between the car and the wall. Okay. And so some weird things can happen when you have a fixed support and you have another body here that's going to be ramming into that fixed support. Okay. And so we want to make sure that we don't apply the fixed support on the same place where we're going to have contact. Okay. Because what's going to happen is that when the car contacts the wall is actually going to depress a little bit, right? And so if you kind of, if you hit an object against something else, it depresses a little bit. It may not be noticeable to the eye, but we have to give it that flexibility because if we make a fixed support, we're basically going to have a perfectly rigid wall right here. And numerically, that can cause some issues. And so we want to make sure that, we give this wall a little bit of flexibility for it to kind of depress when the car hits it. Okay. And that's kind of another reason why that's another reason why we kind of fix it on the side. All right. Any questions on this so far? Question. So what's the material for the wall again? And so the wall, we just left it as structural steel. And so, we don't really care too much about the wall because we're not computing stresses or anything there. And so I just left it as the default. Yeah. Oh yeah. Oh, one more thing. And so I forgot to do this. And so right now, because the car is actually in contact with the wall itself, ANSYS automatically generated a fixed, a bonded support between them. Okay. And so we don't want this. And so we want the car to be able to hit the wall and bounce off, kind of just like you would expect from a normal car crash. Okay. And so you're going to go under contacts or connections and contacts. Okay. And then the one connection region or the one contact region that you see there, we're just going to go ahead and delete that. Okay. So go ahead and right click on this contact region and just say delete. Okay. And so that's going to delete that contact region. And so now now the car is free to kind of hit it and bounce off. Okay. All right. And so that's the fixed support. Okay. One more support that we're going to add to this car is we need to make sure the car doesn't displace in the Y direction. Okay. And so if I angle the car like this, you can see that the Y direction is vertically up and vertically down. Okay. And so we want to make sure the car doesn't bounce off and kind of clip into the road, because we can imagine that we have road underneath this car. Okay. And so we want to make sure the car doesn't clip through this ground right here. Okay. And by another token, we're also going to make sure the car doesn't actually displace this way too, which may not be 100% accurate. But we need this displacement constraint just to make sure that, we don't clip through the ground. And so we're basically assuming that the car is going to be always on the ground here. Okay. All right. Let me go ahead and get rid of this. All right. And so in order to perform that, we're going to insert a displacement support. Where is that? Displacement. Okay. Right. And then on this displacement support, we're going to require that the Y component of the displacement is going to be 0. Okay. And so, you should have basically this right here. Okay. So the X component should be free. The Z component should be free, but the Y component should be 0. Okay. And then for the surfaces, what we're going to select is we're going to select the entire lower rim of this car. Okay. So all of the lower edges down here, we're going to select. Okay. So make sure you're still on face selecting mode, because even though these faces are thin, they're still faces. Okay. And we're going to select every surface down there. Okay. And so once you've highlighted that entire bottom surface with green, I'm going to go ahead and click apply. Okay. And you can see here that we have 8 faces that we're applying this to. And then they're going to be forced to have a Y displacement of 0. Okay. Yeah.
Would we still apply those conditions to the top surface?
No, so we only need that on the bottom. And so we're gonna leave the top of the car to deform. And the top of the car is going to deform actually quite a bit too. But this is just to make sure the bottom of the car stays in contact with the ground. Yeah. Mm-hmm.
Can I see the spaces again?
Yeah. Mm-hmm. So it's all the ones in yellow. And so it's basically, let me click them again. Go ahead and you can, if you're having trouble clicking these, you can zoom in on ANSYS to help you kind of click on these ones. But yeah, should be all of these surfaces that are in green right here. Okay. So does everyone have the displacement constraint set up real quick? Okay. All right. And so now that we're done with the constraints, okay, remember we're not applying any loads because we don't need any forces. The only thing we need to supply is a velocity to the car going in the negative X direction. Okay. And so we're basically going to be giving an initial condition which makes the car accelerate in that way. Okay. And then, so the way we're going to do this is with the initial conditions. Okay. All right. And so under the initial conditions right here, we're going to right click here and we're going to insert a velocity. Okay. And so what you can see from the tooltip here is that we're going to apply a velocity as initial condition in a transient structural or an explicit dynamics analysis. Okay. So let's go ahead and add velocity. Okay. Right. And so we're going to select the entire body of the car. Okay, so make sure you're in body selection mode. And so let's go ahead and hit apply for that. Okay. And then for the velocity, we're going to define it in terms of components. Okay. And then initially what I want you to do is I want you to supply a velocity of 10 meters per second. Okay. And so 10 meters per second is going to be the same as 10,000 millimeters per second. And so make sure that you put the velocity in the negative x direction, because that's the direction of the wall. Okay. And so we're going to start with the velocity of 10 meters per second, and then we're going to go, and then we're going to adjust it from there. Okay. All right. Okay. All right. So the last thing that we're going to need to set before we set the simulation in motion is we need to set the analysis settings. Okay. And so go ahead and click this this entry right here called analysis settings. Okay. And if you'll notice from the tree right here, you'll see that it has a blue question mark. Right? So remember, whenever we have a blue question mark within ANSYS, that tells us that we need to specify something there in order to get a good result. Okay. All right. And so the main thing that we need to specify, and oops, I did not mean to do that. Okay, there we go. All right, and so the main thing that we need to specify here is this thing called end time, right? Remember, remember from our discussion last week that dynamic simulations are marched forward in time, and so you need to specify, how much time that you actually want to simulate for this simulation. Okay, and so for a car crash, a car crash is going to happen very, very quickly, and so we actually don't need to simulate all that much. Okay, and so in order to kind of keep the simulation light, I'm going to set this end time to be 7.5 e to the minus 4 seconds. Okay. And so that's about 3/4 of a millisecond. Okay. And so, the car crash is going to be over just like that. Okay. All right. And so if you want to have a longer animation, or you want to see kind of more dynamics after that, you can set this end time to be higher. But for just this initial job that we're going to run, 7.5 times 10 to the minus 4 seconds is perfectly sufficient. Okay.
You did 7.5 times 10 to the negative 0.04?
If you just do 7.5 e minus 4, then it'll add the zeros just by default. Yeah.
Okay.
Yeah. Or you can just do 0.00075, and so both of them.
Quick question.
Yep.
For changing, so if we keep the velocity constant and we change the end time, is that kind of like dictating where we're kind of like starting the car? For example, like distance away from the wall.
So the car is actually in contact with the wall already, and so we're giving it a velocity, and so this is going to be we're going to simulate 75.75 milliseconds after the impact occurred.
Like it bouncing off.
Yes, exactly. Yeah. Mm-hmm. Yeah. Mm-hmm. All right, and so if you remember from last Thursday, we talked a lot about things like time steps, right? And so we said time steps is the time step size is kind of an important quantity that you need to specify for a dynamic simulation. Okay, so because it determines so much. But luckily, for users, they provide a really nice automated tool to estimate the time step size. Okay, and so you can see here that these 3 settings here, the initial time step, the minimum time step, and the maximum time step, all of these are program controlled. Okay, and so when you're first starting out with dynamics, I would highly recommend that you just leave this as the defaults. And so once you kind of get used to and you run dynamic simulations quite a bit, you can adjust these. But ANSYS actually does a pretty good job of selecting the time step size. But and so for fairly basic jobs, you don't really need to change these. It's only for really advanced stuff that you need to do. Okay. All right. And so we're ready to run the simulation. And so the last thing we need to add here is we need to add our result fields. And so let me just look at the total deformation. I'm going to look at the equivalent stress. And then let's look at the equivalent strain as well. Okay. All right. But you don't need to have these initially, but it'll save you a bit of time later. Okay. But to start off with, I'm going to look at the total deformation, the equivalent stress, and the equivalent strain. Okay. All right, and so, after you've applied the supports, after you applied the velocities, and after you applied the initial conditions and all the result fields, we're now ready to click solve, okay? All right. And so remember what I told you last time, that dynamic simulations are a lot more expensive than static ones. And so we're gonna be sitting here, you're gonna be sitting there for a little bit while the simulation computes, okay? But I will show you something cool. And so while the simulation is running, I mean, first of all, you can check in the bottom left. And so this will kind of tell you, the progress on how the simulation is going. Okay. Right. And so you see right now mine is 12% done. Okay. But if you want to see something cool, what you can do is you can click on solution information here. Okay. Right. And so right now, what it's showing you is kind of the raw solver output. And so this is useless. And so, this normally means absolutely nothing to the average user. But what I want you to do is I want you to go to solution output right here. Okay. So you can see right now that the setting is set to solver output. And I want you to change this to energy summary. Okay. All right. And so with energy summary, let me show you, what you're looking at here. Okay. And so in blue, this curve right here is showing the total amount of kinetic energy in the system. Okay. And so, initially, and so you can see that the x-axis here is time. And so at the very beginning parts of the simulation at t is equal to 0, you can see that our kinetic energy is really high. And then all of our other types of energy is really low. Okay. And the reason for that is, remember, the initial condition that we're giving is that we're making the car kind of have an initial velocity heading towards the wall, okay? And so all of our energy in the beginning is purely kinetic, okay? And then once we get away from the initial conditions, you can see the kinetic energy in the system is going to start to go down, okay? And meanwhile, this purple curve, which is called internal energy, this one is going up, okay? And so what's happening here is that, right at the beginning, the car is going to impact the wall, okay? And as the car impacts the wall, the car is going to start to, deform, okay? And so it's going to start to crumple up, okay? And so as the car crumples up, it's obviously going to start to slow down because it's contacting the wall. Meanwhile, the internal energy, or I would say the strain energy in the system, because the car is crumpling up, what that's telling us is that all of the kinetic energy that we had at first is now going into deforming the car, okay? And then eventually, we reach kind of a maximum here where like the kinetic energy goes down to, not 0, but close to 0. And our internal energy has gone up to, maximum, okay? And so this is kind of the point where we achieve kind of maximum deformation in the car, okay? And so the car is kind of crumpled up, okay? And then, our kinetic energy is low. And so what happens next is maybe not the most realistic thing in the world, but it's kind of a result of all the linear stuff that we've been doing. And so after the car reaches its bottom right here, then you can see the kinetic energy starts to come back up. And so what's happening is that the car is kind of bouncing off the wall and kind of acting like a spring. And so the car is kind of crumpling up, and then it's kind of bouncing off again after that. Okay. And that's what you're kind of observing here. Okay. And so the car is bouncing back. And it's kind of, bouncing back and kind of oscillating like a spring. And so I would say kind of after this point right here, the simulation becomes a little bit, less realistic, because normally you would expect the car to buckle and kind of just stay deformed. But, because we're using linear material model, linear elements and all that stuff, then the car basically acts like a spring. Okay. Okay. And so while I was stalling for time, the simulation finished, okay? And so we can now look at our results. Okay. All right, so let's look at the total deformation, okay? All right. And so the total deformation is going to show, what parts of the car are deforming the most, okay? And so right now, this is kind of boring. So let me go ahead and click on this play button right here, okay? Right. And so this play button is going to play our animation. Okay. Okay. And so you can see the car is hitting the wall and it's kind of bouncing off. Okay. And so you can see, not much is really happening because the car is hitting the wall and it's kind of, not really doing much. Okay. So let's look at the equivalent stress. Okay. I think that one's going to be a little bit more exciting. Okay. Okay. And you can see the maximum equivalent stress that we obtained here is about 700 megapascal. Okay. And that occurs right about maybe like right here. Actually, let me go ahead and turn on the max button. Okay. Where is the maximum stress? I think the maximum stress is occurring maybe somewhere around here. Okay. Okay. And that's it. Okay. And so that's how you do dynamic simulations. Okay. And so I'm going to go ahead and let you guys play around with this for the rest of the class. And if you're having trouble, I can come around and help you out. Okay. But that's all the way up until problem 4 of the assignment. Okay. I mean, granted, you have to produce screenshots for these things, but I want you to start working on problem 5. Okay. And so problem 5, if I can go back to the document here. Okay. In problem 5. What I want you to do is I want you to find the maximum velocity that the car can go before it yields. Okay, and so what we're saying is a yield point is when we have a maximum equivalent stress of 55 megapascals. Okay, and so you can see here that we're way past this point right now, and so you can see the maximum equivalent stress is about 700. Okay, and so I want you to change the initial velocity and rerun the simulation until you get a maximum equivalent stress of less than 55 megapascal. Okay. Right, and so you're going to go to the velocity here, and instead of negative 10,000, you're going to change this down to let's say that minus 1,000 here. Okay, and then rerun the simulation, and then see what the equivalent stress is. Okay, and I want you to play around with that until you reach 55 megapascal. Okay. Problem 6 of this assignment is I want you to basically redo problem 5, but instead of an aluminum car, I want you to change the material of the car to polyethylene. Okay, and so I'm basically going to have you simulate a plastic car. Okay, and so you're going to change the material, and then you're going to play with the velocity until you reach a maximum equivalent stress of 5 megapascal. Okay, and then that's it for the activity. And so once you're done with that, you can just summarize your results, and then it'll be on your way. Okay, and so if you're lucky, and so if you're lucky in terms of the velocity that you choose. You could probably knock out all the data collection for this activity today. And then the only thing you have to do is just, put the screenshots together and submit it for the activity. Okay. All right. Any final questions about the activity? I mean, minus errors and stuff like that. So I'll go around and help for errors, but any questions on just, what you're supposed to do for this activity?
Yeah, just to kind of like get it straight for the car hitting the wall. So what's the difference between like setting it a position away and then kind of like just saying, oh, we're gonna see from after 20 minutes impact?
Yeah, and so if we started the car a little bit farther away, then it would take the car some time to impact the wall. And so in this case, because we're kind of interested in all the stuff that's happening after the crash. We're starting the car basically right when it's in contact. But if we did start the car a little bit off, then the first few time steps of our simulation will be the car is waiting to contact the wall, and in essence that's that would be kind of wasted time because then we wouldn't see any stresses or we wouldn't see any strains at that time. And so I positioned this car basically right next to the wall so that right when we start the simulation, then we start to see interesting behavior right away. Yeah.
So then the deformations or the stresses, they're just primarily due to the displacement constraint and the velocity of the car.
Exactly. Yeah. Yeah. So they're all just purely from the impact. Yeah. And so we don't have any loads here, so we have no forces or anything. And so the only thing that's causing the stresses and the strains is the velocity of the car. Yeah. Yeah. Mm-hmm. Okay. So I got 7,700 megapascal, but I will say that this activity in particular is very sensitive to the mesh. And so I've seen people with even if you use the exact same mesh settings as me, you might get a mesh that's slightly different, and you might get stress values that are very different from that. And so this activity in particular is very, very sensitive to the mesh. And so if you're not getting the exact stresses that I'm getting, then don't stress about it. It's just kind of the nature of this activity. And so remember what I said, that dynamics is normally a very, very hard thing. And so normally a lot of the time that you spend on dynamic simulations is kind of debugging errors like this. And so unfortunately we don't have the time in this class to really dive into all that stuff. But I did want to just introduce the concept to you guys and introduce the features. But don't take the results of this too seriously. That's kind of what I'm saying. Yeah. Okay. All right. So if you're not getting any errors, I would say go ahead and go for it. But if you are getting errors, I can go ahead and help you out at this time. Okay. All right. So Stephen, are you getting same errors as Isaac with the time step error?
No. I'm getting an error that says an error occurred with the post processor attempted to load a specific result.
Oh.
And so I tried rerunning the thing, but it won't even let me rerun.
Oh. Okay. Let me. Why don't you go ahead and share your screen, and then let me see. I haven't seen that error before.
Yeah, so my message is down here at the bottom.
Oh, it looks like a file might have got messed up or something.
Yeah.
Let's try this. Let's try deleting all of the total deformation, equivalent stress, equivalent strain. Okay. Go ahead and insert a new one. So go ahead and insert a total deformation. Oh, still, huh? Try clicking on solve again. Let me see what happens.
Yeah. An error occurred with the post processor attempting to load a specific result.
Okay. So go ahead and delete total deformation again. Try clicking solve right now and see what that does. It's not doing anything.
No.
Let me check your analysis settings. The one right above fixed support. Let me look at that one. Okay. That's weird. Click on solution information. It's right under solution A6. Up.
Yeah.
Okay, so it ran.
Yeah.
I increased my element size, and that worked. Like I guess my computer just couldn't handle 5 millimeters.
I see. That's true. That's true. I think if you change the element size and you maybe not for the car, but try for the wall. And so let's reset this. I think we want to reset the mesh, and then we'll try running the simulation again.
So
go ahead and change this to like
wall.
35, like 35 or something. Yeah. Okay, so we'll go ahead and regenerate the mesh. All right, and then let's just add one result. So let's click add total deformation. Okay, so now click solve and let's see. Okay, so at least it's running. Okay, so while that's running, let me go help Isaac, because I think he had a different issue.
Yeah.
All right, Isaac, you said you received an error time step too small.
Yeah. Let's see.
Was your end time 7.5 times 10 to the -4?
I don't know.
Do you want to share your screen so we can take a look?
Oh yeah. Let's see. Share screen. Oh. Okay, there we go. Okay. So my time step is 7.5 e to the -4. Is that
okay?
Right?
Yeah, that's fine. That's what it should be. Go ahead and click on analysis settings, so right under initial conditions.
Analysis settings, initial conditions.
Okay. Yeah, all of this looks fine. Let me click on initial conditions for me. Oh, I see. Okay. So I think you put the velocity under a different place. So go ahead and delete that velocity right there. And so I want you to right click initial conditions. Not there. Run one below it. Yeah. And then go ahead and insert and then velocity. And so this is where you input the velocity here. And so go ahead and change that to components, or you can select the car first. Yeah. Go ahead and hit apply.
Oops. Apply. Change this to component. Oops.
Yep. And then for the X component, you can do. I know in the document I put minus 150 meters per second. That's like the speed of a speeding bullet, and so it's actually kind of funny. So you can actually run it and see what it looks like. But for the for this one, I changed it to much lower. But it actually looks cooler if you do a higher velocity. So, but it's also going to get you further away from the assignment.
Okay.
It does look cool, and so I would recommend you watch it first. But okay, yeah, let me know how that goes and see if you get it. Yeah.
Okay. All right. Thank you.
Yep. And so I think you have to go to the top of the screen and hit stop share. Yeah.
Stop share.
Okay. Let me go ahead and answer a question in the class, and then I'll come back. Stephen, let me know if it works for you. Yeah. Yes. Usually if you stop it, it'll stop it at the place where that's the next. If you just click stop, it should be.
No, it's the reason. Oh no.
Yeah, you take it as a maximum.
Right where
You don't have to be.
That's right.
Yeah. Yeah.
But all the problems happen during. Check. It's really helpful.
That's weird. I mean, I can see it.
Oh, it looked like it's solved, like,
Okay.
let's see, check.
Okay.
It's good to follow the process. Follow it along.
Yeah.
Oh, yeah, I wouldn't worry about it. It's probably not a weird. It's just probably weird. Obviously.
That's good.
Okay. Okay. That's good. All right, Stephen, did it work out?
No, I didn't like that. Same error.
Really? Same error. Okay.
Well, it says it may not contain.
Wait, Brandon, you had the same issue too, right? But then you said you changed the mesh on the car and it worked out.
Yeah, but I decided to go back to 5 millimeters and increase the wall to 35, like you said, and it worked. But for mine, I added tetrahedron elements or whatever to the car.
Okay. Okay.
I don't know if that caused issues, but now it's working for me.
Okay. All right. Yeah, Stephen, why don't you try that and see if that works.
Did you tetrahedron for the thing? Okay. Brandon, you said you did tetrahedron elements
for the car, and then I just did hex dominant for the wall, but honestly, you could probably go without that.
All right, I'll try that.
Mhm.
start making them go wrong. It's like a machine of plastic.
Oh.
Plastic that you can machine into a CNC.
I seen one of the parts was a pretty yeah, not 100%.
Yeah,
Mhm.
so some of them are actually.
Why isn't that the wall that's to form out?
Yeah.
It's basically zero.
So the wall is first of all, it's made of a much stronger material, and so it's a structural steel. And the car itself is very, very light. And so even though we're applying a metal to it, it's basically just the frame of the wall of the car. And so, because of that, we have something really light. And so that's basically not enough inertia to make any dent in the wall. No, that's it for today. And so, that's basically the end of the activity. And so, I promised a chill activity, and that's as chill as it is. I do have one minor point that I want to state after this one finishes. It's just in terms of interpreting the results, but right now you have everything you need to complete the activity. Yeah. Yeah, basically, and I'll kind of speak now, just, in case people have to run, but, the total deformation field in this one is a little bit deceiving, because it might give you the sense that it's deforming a lot more than it is. The reason for that is, the way deformation is computed is it takes the initial position of where the mesh element was, and then it computes it, it subtracts it from the final part. Yeah. And so, when you look at the total deformation, you might see something where like the whole car is having huge deformations. But that's not really true, because the or it is true, but the reason it's true is because the car actually has some velocity and it's moving away from its initial position. Okay, and so if you want to get like a true sense of deformation, kind of like in the same that we got from static simulations, you would have to look at the strain instead. Okay, so remember, the strain is kind of a relative deformation of kind of the initial configuration. Deformation is just the raw, how far did this point travel from the initial one? And when you have a dynamic simulation like this, the total deformation is usually not as reliable. And so, I would look at the strain field to see, how much is the car itself deforming versus the deformation. Yeah. That's the last point I wanted to make. And then, everything else is, if you want to do the rest of the activity now, I think you can finish it. But if you have other stuff to do, then you can head out too. So. Okay. All right, so this is what I'm talking about with the deformation here. And so you can see, it looks like the whole car is deforming a lot, but the only reason for that is, because the car is just traveling a huge distance away from its initial point. Right? And so in this particular case with the with the deformation, I gave it a huge initial velocity here. And so the car is actually bouncing off the wall and kind of traveling backwards. And so that's why in the last phase right here, if I can kind of pause it in the right place, right? And so in the last phase right here, the car looks like it's deforming a lot, but that's only because the car bounced off and it bounced off by this amount, from the wall. Yeah. Yeah, it looks like the car is made out of jello. Yeah. So this is what happens when you give an initial velocity of 150 meters per second. Yeah, so the reason I have that in the activity is because I think this is the coolest. This looks a lot cooler than before, but it's also very unrealistic, because if you 150 meters per second, that's like the speed of a bullet. And so if you shoot a car at the speed of a bullet at the wall, the whole thing should just crumple. But you can see it just kind of just jiggles and jiggles and jiggles instead.
I know, like what you're saying is that it's not like representing the metal.
The main thing is we're not representing buckling. And so we're basically assuming that the material is a linear elastic material. And so basically what's happening is that when the car impacts it, it goes up that stress strain curve. And then when it's done, it just comes right back down that curve. Like that. And so, you know, there's no plastic deformation, there's no buckling or anything that's happening.
Okay.
And that's mostly for cost reasons. And so if we turn that stuff on, you know, you would get a more realistic simulation, but it would take, you know, a lot longer to solve. Mhm. What about slapping a chicken with your hand? Yeah, that's you know, I saw that video. I saw that video of the guy. He made a contraption to slap a chicken to try to cook it. It was very fascinating. But the whole time I was like, why would you do this? You waste a perfectly good chicken. And like I wouldn't even. I think he succeeded, right? I think he got the chicken up to a temperature which is safe enough to eat. But the texture was just disgusting. And so I would not want to eat that at all. So the reason mine looks like Jello is because I gave it an initial velocity of 150. And so if you're following kind of the lecture, I think I only gave this an initial velocity of like 10 meters per second. And so, you know, that's a lot less. And so if you want to make it look like Jello, you have to give it a huge initial velocity of like 150. And then that'll give you that. But it also gets you way far away from the objective because, you know, what we're assuming is that this car is going to start to yield at 55 megapascal. And you can see here that we're very far away from 55 megapascal. Actually, let me go ahead and switch this to millimeters so we can see. And you can see here we're at 6,000 megapascal. So we're 2 orders of magnitude away. Yeah. Mm-hmm. All right, and so that's the activity. And so, you know, we have 20 minutes left in class. And so legally, I'm required to be here until 6:45. And so, you know, if you want to do the rest of the activity at home, you know, by all means, you can go for it. But, you know, I'll be here until 6:45. And so if you have any questions on this activity, or if you want to run an idea for a project by me, you know, I'd be happy to hear that and give you feedback on that. Or a question about anything else too. And so, you know, I'm happy to answer. So. Yeah, and so yeah, go ahead and ask away if you guys are having questions. Yeah, step file works good. IGS works really well too. STL also works, but I don't recommend STL because STL you kind of lose a lot of information in the file form. So STL is very compact, and so it doesn't take up a lot of space. But you know, if you're switching between SolidWorks and ANSYS, you want to transfer as much information as possible. Yeah, both should work. Yeah, I think both step formats are fine. Are just fine.
Question regarding the announcement you made the other day.
Yep.
So when you say to not do a conceptual question, ask about the concept of symmetry.
Yep.
You just mean that specific problem not to do.
Just that one, yeah, just 1B. Yeah. So the other 3 you should be able to answer. It's just 1B that you can't. Yeah, we'll talk about symmetry probably after Thanksgiving. You know, because it is actually a really useful tool for finite elements. It's just I kind of had to skip it at this point just because we were a little bit behind. So
basically what that does is kind of like you can find symmetry in your simulation in about like half of your simulation time.
It does, yep. And actually you can actually apply symmetry for this problem here. And so if you look at it from this perspective, right, you can see here that if I drew a line right down the middle here, okay, we basically have the exact same, I mean, imagine I drew the line better. right? And so if I drew the line straight, you can see that the car on the left of the line and the right of the line is exactly the same. And so we could actually cut the cost of the simulation in half by just by making a cut here, and then just simulating just one half of the vehicle. And so what that allows you to do is that, just in a very naive sense, it cuts the number of elements you have in half. But because of that, you can take those elements that you save and pack them into this area again too. Right? And so it'll let you basically refine a lot more than what you could before, because then you're only simulating half of the geometry. Yeah.
And then whatever happens on this side, that's not on the other side.
Exactly. Yeah. Yeah. Hmm?
Thank you. And the other thing, so for 3D, we just set up the global linear system and we're good.
For 3B, that's the crane one. Let me see. I think for everything in the homework, I do want you to solve everything, if I'm not mistaken. For the exam, you don't have to solve anything. And so for the exam, you can just set it up. Let's see, 3. Oh, I'm sorry. Yeah, I always forget. I forgot to renumber this. So this should be problem 4, obviously. So you're talking about this one or this one right here?
So there's 2 3Ds?
Yeah, so the 2D truss problems are I have problem 3, and then the very last one I forgot to renumber this, but the beam problem should be problem 4, not problem 3. Yeah.
Well, I guess whichever one you were referring to.
Oh, this one. Yes, yeah. So for this one, yeah, you just have to set it up. And so if you try to solve this one, you're actually going to get it's going to throw an error in your map. So this one you just have to set it up.
Okay, so the original 3D.
Yeah, the original 3D. Yeah. Mm-hmm. Yep. Mm-hmm. If you're 55.68, that's close enough, and so that's already super close, and so that's perfectly fine. Yeah. Yep. Yeah. If you're within 10%, that's fine, especially because I know these simulations take a while to run, and so don't beat yourself up over like 0.5 of a megapascal. So if you're within like 53 to 57, that's perfectly fine.
Thank you. Have a nice week.
Thanks, you too. Oh yeah, have a great weekend, everyone. And so remember, we don't have class Thursday, so next time I see you guys will be next Tuesday. So enjoy your day off, and I'll see you next week. Yeah, let's wait. Yeah. Okay. Okay. Perfect. No, I love it. Yeah, I think that's hopefully someone do that. I believe it's under. Yes. Yes. Do you have a partner?
No, I might send shoot a message to see that.
Okay. Yeah, I'll reserve that for you. This course. Oh yeah. Okay. No, I think that's great. I think that's then you have like really extreme external forces, external spaces, and really interesting body configurations too. So I think. Okay.
Yeah.
Oh, yeah, they're like, similar to-
Yeah. Yeah. Someone pointed out to me, that was kind of a mistake on my part. I actually planned to give you guys a different version of the geometry, but the one I gave you was already in show. But that's okay. I was gonna convert it and so I try to fix this out.
Yeah.
Oh, I think if you open up it, we can. This might just be display. So I think because when you define it, you have to draw the cross section. And so you can have it display with the cross section just for visual. But in actuality, it's just a so I think they're just showing visual. So yeah, for this one, and the reason I picked it was because we had active before, but with the shells and beams, so I was gonna have to inventory. But we already did it. Yes, yes. Yeah. Yeah. And so you can see the thickness that they apply here, and you can compare that to the thickness. Normally you would measure. I think this geometry is creating a space point, and so you don't have sketching. If you open up a space point, you can measure this, so you can use the measure tool. Click on right here. Like click on this.
That's what we're detail.
Or quick measure. So you can see that. 6,000, almost 6,000. And the thickness was like 5 inches. Yeah, yeah. This one definitely. Yeah. Space is also not better for measurements. The design mod where it's unless you're creating the dimensions within the design mod where it's hard to measure stuff. But space has a really nice measure. Even if the model was created in design, you can open an open space and just that's usually. I'd rather get those. Yeah. So I can see, right? Okay. Yeah. I think probably those two codes is probably yeah, that's very hard to do. But if you're not able to, you can do is you can take the and then where that's the side. So yeah, so you get a little stuff. So we try like not even two. Yeah, so we're gonna use that. So unless you sort of want more, I would definitely try to. But I'm not sure exactly. Yeah, we'll see how far. Good idea. I'd say this is kind of the best time. Oh, yeah. Oh, yeah, I think that's probably not just zero. So you did right on non-linear analysis. That's usually where I turn it. Actually, I think probably both. I think probably both. Okay. Would be interesting to see try one with the bond. Very awesome. So and the connection, but the connection, having nonlinear connections is probably not valid because we don't expect these to
No,
No, we don't. I mean, normally we expect these to be pretty cold. So we have failure for some reason. But for these ones usually connect. I think on the finished spot. So that make it you could assume that they're close. So when I say that it's not near contact, friction is frictional or so nonlinear contact actually have a separation. And so as long as we don't have any separation, that can say that we bond the contact. So for these ones, I wouldn't expect there to be any separation. Any nonlinearity that I would expect would be either from the material or from the actual structural mechanism.
If the materials and the factors can be, but at the same time, you can also have
exactly. Yeah, so you can have all three of them. Some could be nonlinear, some could be linear. But yeah, for this one, I would not expect any separation. I would just keep all that. Your reasons.
and I had seen this and also it's in the 49 systems because
you can do it several ways. It's very symmetric.
and just multiply the cell phone. That's it.
Yeah, you just assume that it's exactly the same. Yeah, you have to be careful. So, when you do symmetry, you assume that everything is symmetric. So, let's say that you're doing this full model right here, and you only want to apply a load right here. You can't do this symmetry right here, and that is you have the same load. And so that's what you want. That's good. If you don't want that, then you can't. 80%. Yeah. All right. All right, so we're out of time, and so I know not that many